All right, welcome to our third pre-lab video for the 12-12 lab this semester at North Georgia. This week we're going to be taking a look at the determination of molar mass by freezing point depression. So first off, freezing point depression in terms of exactly what it is and kind of how it works. It's something called a colligative property, which is any property of a solution that depends only on how much basically stuff is dissolved in that solution and not on what that stuff actually is. So the only thing that matters is really just how many total particles end up dissolved in the solution, and that's what's going to impact the property itself. So in the case of freezing point depression, the more things that you dissolve in water or any other solvent, the lower the freezing point is always going to get. So for a quick look at kind of why it happens that way or why freezing point goes down as we add more things to a solution, remember that for any solution or really any liquid in general to freeze, you need to make new intermolecular forces to hold solvent molecules together tight enough to make a solid. But the more and more stuff that you add to your solution that isn't the solvent, you're basically going to make it harder for the solvent molecules themselves to organize in the repetitive structure they need to get that solid as a result. So the net kind of end result of all of this is that the freezing point itself goes down because the temperature has to get lower than normal so that the particles are moving even slower than normal to actually be able to interact with each other for the solvent molecules and form the solid. And that's going to be true for any solution when you add things or dissolve things in it. The more stuff dissolved in that solution, the lower the freezing point is going to go. It's why we put salt in the roads, for instance, in the winter, to try and prevent ice from forming. We're just hoping to lower the freezing point of water by enough that the water doesn't freeze in the roads. That's kind of the point behind that. Now, calculation-wise, how can we calculate freezing point depression? We can use the equation shown here. So the change in freezing point, that's the delta TF, is going to be equal to negative I times M times K sub F. So these pieces, K sub F is a freezing point depression constant. It's going to be specific to any particular liquid. So every liquid that's going to be the solvent is always going to have its own kind of unique individual freezing point depression constant. The little m is actually not mass in this case, it's actually molality, which that is not a typo. It's not molarity, it's molality instead. Where molality is, it's very similar to molarity, but it's moles of your solute divided by kilograms of solvent instead of the liters of your total solution. Now, the reason molality has to get used here instead of molarity is that molarity can actually change slightly with temperature. And since we're looking at trying to measure a temperature change, we need a concentration that doesn't change with temperature. And so molality is that concentration that won't change with temperature because it has a mass of solvent basically instead of a volume of a solvent, which will change if you heat it up or cool it down. So that's why we have to use molality here. Now, the I in this equation is something called the Van Hoff factor. And this kind of goes back for colligative properties. Almost all colligative properties will have this I show up somewhere in their calculation, basically, for any calculations dealing with colligative properties. And it's a measure of how many particles a compound is going to break into when it's dissolved in a solvent. So for covalent compounds, for pretty much everything we see, the I is always just 1 because they don't really have any particles to really break into when you dissolve them. They just dissolve the individual molecules and that's it. Really, the Van Hoff factor is most important for ionic compounds. In particular, if you're putting them in aqueous solutions, if you put sodium chloride in water, it breaks apart into 2 ions, 1 sodium and 1 chloride, and so as a result, I equals 2. If you were to put calcium chloride into water, it breaks into 3 ions because you get 2 chlorides and 1 calcium, so now I would be 3. And do pay attention to the fact that it's the number of ions, not just atoms. So if you get something like calcium carbonate, which is CaCO3, that would still be an I of 2 because there's only 2 ions that are actually being formed in that case when you dissolve it in water. Now, visually, what we're going to be seeing and kind of looking for in this week's lab is we're going to be trying to measure the freezing point of naphthalene. And we're going to measure it both just as pure naphthalene and then also with different mixtures. We're going to dissolve other things in the naphthalene and see how the freezing point changes. Now, how we're going to go about finding freezing point is actually by recording data. We're going to heat naphthalene up well above its melting point by using a hot water bath. And so what we're going to do is actually watch our temperature decrease once we've got all our naphthalene melted. We're going to take it out of the heating source. And as the temperature decreases, eventually it's going to hit a point where the temperature kind of either levels off or maybe even actually increases a little bit again. And ideally, we should see this slight increase. This is going to come from basically those new intermolecular forces that I was mentioning a couple slides ago that have to form in order for a liquid to freeze. Because if new intermolecular forces are forming, that's energy being released, that's going to cause the temperature to actually go up a little bit again. And so we, in a perfect world, should see this little spike in temperature after the temperature's been cooling down for a while. And we should see this little spike in temperature about the time that we actually see our liquid start to freeze over, kind of cross over from being a liquid to a solid. Now, ideally, we'd see this, but the reality is we probably won't see this actual little increase in a lot of our trials, or at least not in all of our trials. What might happen is instead of coming down and going back up, it might just come down and then just level off and then go back down again. Or it'll be decreasing, decreasing, decreasing. It might even keep decreasing, but decrease at a slower rate and then go back down again at a sharper angle. So we're looking for where does that temperature change kind of like alter its course in terms of its constant decreasing that it had normally been doing, and that will help us try and identify where our freezing point is. And what we'll look for, if we do see this little rise in temperature that we saw here, there's this little rise, kind of where the blue is the peak of that, where it rises back up to, that's what we actually call our freezing point for that particular liquid. Like I said, a lot of times we're not going to see that rise. That's okay. We're just looking at the plateau. Wherever we see our plateau as our freezing point instead. Those are kind of the pieces that we're looking for out of kind of the graphical data, because we're basically going to have information like this that we're going to record in lab. We're going to use our lab quest to do that. We'll be recording temperature over time, looking for kind of, like I said, that plateau or that little tiny rise back up to identify where our freezing point is for a substance. Now, quick setup thing here. This is kind of quick image from your lab reading as well. As far as what things are going to look like, you're going to have a hot water bath. You want to make sure you have a stir bar in the hot water bath just to kind of keep the temperature a little more even throughout the hot water bath, hopefully. And what you're going to do is you're going to have a test tube set up that's going to be in a clamp. And then inside the test tube, you're going to have your thermocouple to measure temperature. We're going to have naphthalene in here as our solvent that we're going to be using for all of the parts of our experiment. And you're just going to want to make sure that the naphthalene in the test tube is all completely submerged in your hot water bath. If it's not, then all the naphthalene doesn't really get heated evenly, and it kind of makes things a little bit awkward in terms of when you actually start to cool it down, because you don't have a constant temperature really throughout the solution. And then the one thing with this setup, dude, that I would really kind of make note of to try and make sure you kind of avoid is don't let the thermocouple sit on the very bottom of the test tube and then have the test tube sitting in the bottom of the beaker touching the hot plate with no stir bar in there. That's a recipe for destroying your thermocouple because it's just exposed to too much heat. So just make sure you got a clamp kind of holding the test tube up a little bit from the bottom. Make sure all the naphthalene's submerged below the water bath height, and then you can clamp, get a secondary clamp for your thermocouple if you want one. It's probably not needed as long as your test tube's not like I said, touching the bottom of the beaker for your water bath. Should be okay. Now, the parts of this experiment, there's going to be three main parts. The first part's going to focus just solely on finding the freezing point for pure naphthalene. So that's basically looking at the plot like what we kind of showed a couple slides ago and just picking out the freezing point for pure naphthalene. And then there's no actual real calculations to that part of the experiment. So we're looking for that small rise or maybe that plateau to find the freezing point. And again, if we don't see that little rise, that's perfectly fine. It's actually fairly normal for a lot of these experiments. Now, the second part of this experiment will have some calculations involved with it. And our goal is to find the freezing point depression constant for naphthalene in particular. So how we're going to do this is we're again going to do basically the same experiment where we heat the naphthalene up till it melts, let it slowly cool down. We're going to observe the temperature over time, look for that kind of sharp rise or plateau again to identify our freezing point. But this time we're going to have, before we did that part of the experiment, we're going to have added a little bit of biphenyl as our known compound to our naphthalene. And we'll have a mass of the biphenyl that we added as well as a mass of naphthalene so that we can actually calculate our molality and eventually use our equation here for freezing point depression to calculate the freezing point depression constant for naphthalene itself. And then that is going to be something that we use in kind of the third experiment for the calculation. So just to kind of reiterate what's going on here, for our case, I is just going to be 1 because naphthalene and biphenyl and all of the compounds we use in this experiment are covalent. So the Van Hoff factor is just 1 for all of them because they don't break apart into further pieces. Little m again is molality. So if we have a mass of naphthalene and a mass of biphenyl, we can convert the mass of biphenyl into moles of biphenyl. We can convert the mass of naphthalene into kilograms of naphthalene. And then we can use those two pieces to find our molality. Kf is what we're going to solve for. Our change in freezing point is going to be whatever the freezing point for part 2 of the experiment is minus the original freezing point from part 1. That should be a negative change. And that's why there's a negative sign in this equation, is because delta TF is always going to be a negative value. So all of these values like I, M, and K sub F are all positive values, so you have the negative sign in the equation to kind of balance that all out. All right, and then the last part of the experiment, the third part, we're going to do one more kind of a heating and melting cycle. And for this third part, what we're going to do is actually add, we actually do know the compound, we're going to add benzophenone, but our goal for the experiment is going to be to find the molar mass of benzophenone in this case. And since we do know the identity of the compound here, it's going to be more for kind of calculating how accurate we can get and seeing how close to the real molar mass of benzophenone we can get from our experiment. But we're going to add kind of a measured amount of benzophenone to the naphthalene. We're again going to go through the same steps to determine the freezing point of our new solution. And then again, we can use that same freezing point depression equation to go through and eventually find the molar mass, hopefully, for benzophenone. So how this part of the calculation works, since this is kind of the longest one, this time we'd really be solving for the molality in the equation. I is still 1. Our delta TF this time should be the freezing point here from part 3 of our experiment, minus the original freezing point in part 1. For the K sub F, we're going to use whatever we calculated from part 2 of the experiment, so we can find molality. And molality for units is moles of solute over kilograms of solvent. But since we know the actual kilograms of solvent, or really the mass of naphthalene we're going to use in this part of the experiment, and we can calculate the molality from this equation, we can actually figure out how many moles of our solute must have been added to our test tube. And then if we know how many moles were added, and we have the original mass of the benzophenone that we add to our solution, then if we just take the mass of our benzophenone divided by the moles that must be in our solution, now we can find our molar mass. So that's kind of our step or progression walkthrough of how we're going to find the molar mass for the benzophenone in this experiment. And those will be kind of the main post-lab calculations that you'll be doing. Last couple notes on waste for this lab. So nothing can go down the sink. Naphthalene, for those that don't know already, is kind of the main ingredient in mothballs, so they stink pretty bad. It's not something we can actually sit down the sink. We have to have kind of specific waste collection for it. But there are a couple things that as you get ready to dispose of your waste to kind of keep in mind. You're only going to be getting rid of the materials from the test tube after trials 2 and 3. For trial 2, you're actually just using all the naphthalene you used in trial 1. All you're going to do is basically remelt it all, and now we're going to add some of that biphenyl to it, and then just repeat the process. And then after trial 2, you'll go ahead and dispose the contents of your test tube, probably get a new test tube, and then get new naphthalene, and then you're going to do part 3 of the experiment. But for both trials 2 and 3, when you're done with them, to get rid of the naphthalene, you're going to have to reheat it one last time to melt it, and then kind of quickly take it over to the waste and pour it out before it all resolidifies. And so you'll want to do that relatively quickly, but also obviously carefully so that you're not like running over other people in the lab, because people will be moving around. So, and if the test tube doesn't kind of come perfectly clean as you do this, don't panic. We have other ways that we can clean these. We'll have some acetone there that we can use to dissolve and rinse out the naphthalene. And if it's really bad and there's a lot of naphthalene stuck to the tube, we can actually just burn the naphthalene off in a furnace then later in the week. But the biggest thing is just that all of the waste from the naphthalene is going to get collected. And as you're doing this, try not to spill the naphthalene at different spots, especially outside the hood. The stuff smells bad enough just from heating it up and cooling it down. If you start to spill it in other places, then it's just going to spread the smell all over. So everyone kind of has to suffer through it equally. So do just kind of take caution while handling it all throughout the lab, so that hopefully it doesn't get worse for people kind of throughout the week. All right, thank you, and hopefully everyone has a good week in lab.